Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. This second video lecture is the continuation of my first video lecture for week 16. In first video lecture, we have discussed already the derivation and interpretation of Euler methods. Now, in this video lecture, we are going to discuss the Euler method by solving some numerical problem. I have already told you that Euler method is used for the approximate numerical solution of the first order differential equation. So working rule for this Euler method is we have a function. Given function is taken for the first approximation using initial boundary condition and value of h. If the value of h is not given, then the initial and the final value, which is required value, is divided into n sub intervals for finding value of h. After getting the first approximation, the second approximation is taken for the function of x0 plus h and y1. Then the Euler method become y2 is equal to y1 plus h if at x0 plus h plus y1, where y1 is the value obtained from the first approximation. Similarly, approximations are taken out until h0 plus h is equal to xn, and this is the required value of y at any point xn. For example, to apply Euler method to solve this differential equation, y dash is equal to x plus y. So dear students, in the working rule, you see here in the given problem, first order differential equation will be given and its initial condition will be given, like you see over here, y at 0 is equal to 0. So this is the initial condition, and we have to find the value of y at some points of x with the equal step size. So in this problem, the step size is given 0.2. So if the step size is not given, then we distribute the x points to obtain the step size. Now in this problem, the first order differential equation is given, y dash is equal to x plus y. This is equal to dy by dx is equal to x plus y. Now this is f of x. So this is the function f. Now in this first order differential equation, this is the initial condition and this is the step size which is given. Now using the Euler method, yn plus 1 is equal to yn plus h if at xn comma yn. Now this is equation number 1. Putting n is equal to 0, we obtain y1. This is the first approximate solution of the first order differential equation, which is equal to y0 plus h if at x0 y0. So this is now actually x0 plus y0, because this dy by dx is equal to f of xy, where f function at xy is given by x plus y. So now this is xn plus yn, but when we put n is equal to 0, this will be x0 plus y0. So x0 is equal to 0. In this given initial condition, this is x0 is equal to 0 and y0 is also equal to 0. So y1, putting n is equal to 1, we obtain y1 is equal to y0, and the y0 value is 0 plus h value is 0.2, and the function at x0 y0 will be 0 plus 0, because the x0 value, this is x0 value is 0, is y0 value also equal to 0. So the function is defined by x plus y. So function at x0 y0 is equal to 0 plus y, and now after simplifications we obtain the first approximate solution is 0. Now for n is equal to 1, we obtain in this formula the second approximate solution, y2 is equal to y1 plus h into the function at x1 y1. Now putting the value of y1, which is 0, and the value of h is 0.2, and function at x1 y1. Now y1 is actually 0, and x1 according to the step size will be 0.4. So y2 is equal to y1 is 0 plus this is the step size, and the function at x1 and y1 is equal to x1 plus y1 according to this definition. The function is given by x plus y, so x1 y1, which is equal to the function x1 plus y1. So y2 is equal to y1 plus h into function at x1 y1, and the function at x1 y1 will be defined x1 plus y1. So this is the value of y1, this is the value of h, and this is the value of x1. This is the value of the 0.2 is the value of step size, and the value of x1 is 0.2 according to the step size. First of all, you see over here the value of x0, you see here the value of x0 is 0. So the function at x0 y1 will be defined by x0 plus y0. So x0 0 and y0 0. Now this is the value of y1. Now putting n is equal to 0, this will be x1. So x1 value according to the step size will be 0.2. From 0 according to the 0.2, the value of x will be 0.2. Now you see over here, this is x1 and this is y1. So after simplification, we obtain the value of y2 is 0.04. Now for n is equal to 2, the formula will be y3 is equal to y2 plus h if at x2 y2, and the function f is defined by x plus y. So now we obtain here x2 plus y2. Now the y2 value is 0.04 plus this is the value of step size, and the function at x2 y2 is equal to x2 plus y2. The x2 value is 0.4 and the y2 value you see over here is 0.04. Now after simplification, the y3 value is 0.128. Now for n is equal to 3, we obtain the fourth approximate solution for the first order differential equation. y4 is equal to y3 plus h f of x3 y3. The function at x3 y3 will be defined x3 plus y3. So this is the value of y3 and this is the value of step size, and now putting the value of x3 which is equal to 0.6 according to the step size, and the value of y3 is 0.128, and then after simplifications we obtain the value of y4, and this is the value of y3, this is the value of step size, and add the value of x3 and y3, we obtain 0.728, and 0.728 multiplied by 0.2 and then adding 0.128, we obtain the value of y4 is 0.2763. Now putting n is equal to 4, you will obtain the value of y5, and the value of the x will be equal to, you see over here, for y2 the value of x1 0.2, for y3 the value of x3, the value of x2 is 0.4, and for y4 the value of x3 is 0.6, and for y5 the value of x4 will be equal to 0.8. And dear students, try yourself to calculate the fifth approximation solution for the first order differential equation, and this will be actually the solution at x is equal to 0.8. Now dear students, another example to find the initial value problem. For the initial value problem, now another example for the initial value problem, y dash is equal to 9.8 minus 0.2 y. So this y dash is equal to the function f, and the initial condition is given at y at 0 is equal to 0. Now we can use Euler method with the step size 0.1 to approximate the solution at t is equal to 0.1, 0.2, 0.3 and 0.4 as shown you see over here. In this problem, the function is differentiated with respect to t. So t is the domain point, t is the horizontal point, and now we put t is equal to 0.1, 0.2, 0.3 and 0.4 according to the step size. So in the Euler formula, yn plus 1 is equal to yn plus h f of 8 tn yn. Now here domain represented by t. So putting n is equal to 0, we obtain y1 is equal to y0 plus h f naught. So f naught mean 9.8 minus 0.2 y0, and the y0 value is 0, so we obtain the f naught value is 9.8, and the step size is 0.1, which is given in the problem. Now after simplifications, we obtain the y1 value is 0.98. Now for n is equal to 2, for n is equal to 1, we obtain the second solution, y2 is equal to y1 plus h f of f1, mean f8 x1 y1, and but in this problem the domain is represented by t, so according to the formula this will be the function 8 t1 y1, the function 8 t1 y1, but t1 domain is not presented in this problem. You see over here only we obtain 9.8 minus 0.2 yn. So for n is equal to 1, this will be y1, and the y1 value is 0.98. Now putting here y1 0.98 plus the function 8 n1. So if the function at n is equal to 1, we obtain 9.8 minus 0.2 y1, and the y1 value is 0.98, and this is the step size. Now after simplification, we obtain the second solution, 1.94. Now for n is equal to 2, we obtain y3 is equal to y2 plus h into the function 8x2 y2, but the domain you see over here, the domain represented by t, so the function will be 8t2 and y2, and t2 is not presented in the given problem. You see over here, this will be the y2. Now putting the value of y2, 9.8 minus this is the function function value 1.94, and this is the step size value 9.8 minus 0.2 into y2. This is the value of y2, and after simplifications we obtain the value of y3 is 2.88. Now for n is equal to 3, we obtain y4 is equal to y3 plus h into the function 8 t3 and y3. So this is the value of y3 plus 9.8 minus 0.2 y3. This is the value of y3 into the step size, and after simplification we obtain the fourth approximate solution, 3.80. Now dear students, we can compare this approximate solution with the analytic solution with the exact solution of the first order differential equation. In the differential equation, we have already discussed that how to solve the differential problem. First order differential equation, we can solve the first order differential equation by separation of variable, by linear method, and by the homogeneous method. But in this problem, you see over here, we can solve this problem analytically. For the exact solution, we can solve this problem by separation of variable. Actually, y dash mean dy by dt, and 9.8 y dash is equal to 9.8 minus 0.2 into y. So y dash is equal to taking common minus 0.2. Taking common minus 0.2, we obtain minus 0.2 into y minus 49. So this is equal to dy, and dividing both sides by y minus 49, and this is 0.2. Now dy by dt, shift dt to this side. So this is actually the separation of variables. Now taking the integration of this term will be equal to natural log of y minus 49, and the integration of this term will be equal to minus 0.2 t plus c, where c is the constant of integration. Now taking int log on both sides, we obtain the solution y is equal to 49 plus k e power minus 0.2 t, where k is equal to e power c. Now putting the initial condition y at 0 is equal to 0, this term will be 0 and e power 0 is equal to 1, so k is equal to minus 49. And now the general solution is equal to y is equal to 49 into 1 minus e power minus 0.2 t. So putting t is equal to 0.1, 0.2, 0.3, like you see over here in this problem, t is equal to 0.1, 0.2, 0.3 and 0.4. We can obtain the exact solution, the exact value from this exact solution, like see over here in this table. This is the value of t: 0, 0.1, 0.2 and 0.3, and putting all these values in the exact solution formula, you see over here, this is the exact solution. We obtain the at t is equal to 0, the exact solution is 0 and the approximate solution is also equal to 0. And now t is equal to 0.1, the exact solution is 0.97 and the approximate solution you see here at t is equal to 0.1. At t is equal to 0.1, the approximate solution is 0.98. So you see over here in this table, this is the exact solution and this is the approximate solution. Now the error between the exact and approximate solution, you see over here, this is the error, and the percent relative error is given by this formula: exact solution minus approximate solution divided by exact solution multiplied by 100. So this is the percentage relative error. So in this problem, you see over here, the exact solution and the approximate solution are most close to each other. Now another example number 3. For the initial value problem, y dash is equal to 4 minus t plus 2y, and for this problem, initial condition is given: y at 0 is equal to 1, the t value is 0 and the y value is 1. Now for this problem, the step size h is equal to 0.1, and to approximate the solution at t is equal to 1, 2, 3 and 4. As you see over here, y1, putting n is equal to 0 in the formula, yn plus 1 is equal to yn plus h into f at xn yn. But in this function, now the domain is represented by t, so we obtain the function the function fn at tn comma yn. Putting n is equal to 0, we obtain y1 is equal to y0 plus h into the function at t0 and y0. In t0 at y0, the function will be 4 minus t0 plus 2 y0. Now the y0 value is 0. This is the initial. The y0 value is 1. So y0 is equal to 1 and plus 4 minus t0. T0 value is 0 plus 2 into y0. The y0 value is 1 into the step size 0.1. And now after simplifications, we obtain 1.6. Now for n is equal to 1, we obtain y2 is equal to y1 plus h into the function at t1 and y1. So the y1 value is 1.6 plus 4 minus t1. The t1 value is 0.1 according to the step size 0.1 plus 2 into y1. The y1 value is 0.6 into the step size 0.1. Now after simplifications, we obtain the second solution 2.31. Now for n is equal to 2, we obtain y3 is equal to y2 plus h into the function at t2 and y2. Putting the value of y2, 2.31 plus 4 minus t2 plus 2 plus y2. The y2 value is 2.31 and the t2 value is 0.2 according to the step size 0.1. The first value of t0 is 0, t1 is 0.1 and t2 is 0.2. Now after simplifications, we obtain the y3 approximate solution is equal to 3.15. Now for n is equal to 3, we obtain y4. y4 is equal to y3 plus h into the function at t3 and y3. So the y3 value is 3.15 plus 4 minus t3. The t3 value is 0.3 according to the step size 0.1 plus 2 into y3. The y3 value is 3.15 now into the step size 0.1. Now after simplifications we obtained the fourth solution. The fourth approximate solution is 4.15. Now the exact solution for this first order initial value problem, this is actually the linear equation. So the solution for this problem is equal to y is equal to minus 7 by 4 plus 1 over 2t plus 11 by 4 e power 2t. Sometime this exact solution will be given for the comparison of the approximate solution with the exact solution, but if this exact solution is not given, then we have to find the exact solution for the validity of the approximate solution. We will compare the approximate solution with the exact solution, then we can decide that how much the approximate solution is valid. Now for example, you see over here in this problem we compare the approximate solution with the exact solution. The first 10 Euler approximate solution are given in this table on the left hand side. A table of approximation for t is equal to 0, 1, 2, 3 is given on this right hand side table. See text for numerical results with h is equal to 0.05, h is equal to 0.025 and h is equal to 0.01. And at this table the step size is 0.1, and at this table the step size is 0.05, 0.025 and 0.01. So you see over here in this table the step size actually 1, 0, 1, 2, 3, 4, and in this table the step size is actually 0.1. Now we can calculate the result for the step size 0.05. Similarly we can calculate for the step size 0.025. Similarly we can calculate the approximate solution for h is equal to 0.01. Now for h is equal to 1, this is the exact solution and this is the approximate solution. So if we put t is equal to 0 and this exact solution, this term will be 0 and this term will be 11 by 4 minus 7 by 4. Minus 7 by 4 plus 11 by 4, we obtained 4 by 4, and 4 by 4 is equal to 1. So this is the exact solution, and the approximate solution for t is equal to 0. You see over here in the problem, this is given that for t is equal to 0, the value of y is 1. So this is the approximate solution, y is equal to 1, and this is the exact solution, y is equal to 1. So there is no error and there is no percent relative error. Similarly for t is equal to 1, this is the exact solution and this is the approximate solution. And for all values of t, you see over here, these are in this column, this is the exact solution and this is the approximate solution, and this is the error between the exact and the approximate solution, and this is the percent relative error between the exact and the approximate solution. Similarly for step size is equal to 1, you see over here, this is the exact solution, this is the approximate solution, and this is the error, and this is the percent relative error. Now dear students, for this example we below graphs showing the exact solution graph by the red color and the approximate solution by the blue color. So for t is equal to 0, 1, 2, 3 and 4, this is actually for step size is equal to 1. The exact solution graph is represented by the red color and the approximate solution graph is represented by the blue color. So for t is equal to 0, the exact solution is 1. For t is equal to 0, the exact solution is 1 and the approximate solution is also 1. So you see where these points are very close to each other because the error at t is equal to 0, there is no error. So the points are very close to each other. Similarly for t is equal to 1, the exact solution is 19.07 and the approximate solution is 15.78. So there will be some error because for t is equal to 1, you see here this is actually t is equal to 1. T is equal to 1 and for t is equal to 1, the exact solution is 19.07. So 19.07, you see over here 19.07, you see over here, and the exact solution is 15 point something. So 15 point, you see this is the approximate solution and this is the exact solution. Now you see here the error is large, so many errors between the exact solution and approximate solution at t is equal to 1. So dear students, in this video lecture we have discussed some problems by using the Euler method. Now this is the end of this segment. Thank you. Allah Hafiz.